All right, so let's start. Here when we are trying to derive the Richards equation as well as the Solute transport equation, which are the fundamental equations in MS Sutra, a numerical package that solves unsaturated flow as well as Solute transport. So after we derive those equations, we are going to look at the input to see how the input is being implemented. The governing equation is being implemented to the txt input files. What does it? It's being, oh no, it's not. Okay. So there we go. So before we start, we really need to understand one equation, very clear. That is Darcy's law. So basically, Darcy's law is able to tell you how flow transported from one place to the other, and basically the driver is what we call hydraulic head. And the hydraulic head is written as psi is equal to P divided by rho G plus H. And how to understand this equation is that if you have flow, say you actually have a box of water, and in one end you would have the pressure, and on the other hand you would have different pressures, right? So the pressure is actually the force to drive the flow from A to B, for example. But this is not always the case, because you could also have another case where the pressure on both ends is going to be the same, whereas the elevation from the first point is higher than the second, then the flow goes on the other direction. So basically, hydraulic head itself is the head that that drives water flow. The second thing that we normally do in the model is what we define another variable called the pressure head. And pressure head is relatively similar to that as well. So we could call it pressure head. Let's call it H, right? Is equal to P plus rho G H, right? Now, again, we think about a case similar to the left-hand side, that you have pressure from this is the pressure level, this is the P1, and here is P2, and the elevation, let's assume it's gonna be the same, and here is delta x. Then basically, if we try to calculate the delta H, is going to be equal to P2 plus rho GH2 minus P1 minus rho GH1 right? And if we do a delta x here, we do the whole thing, right? And then based on this, we will see that the equation can be written by P2 minus P1 delta x minus rho GH2 minus H1 delta x, right? And you see that this is not really affected by the directions at all, because the pressure P2 minus P1 actually ends up with a value greater than 0, and of course the flow is going on this direction, right? So the gradient, this is the gradient, goes from small to the largest, to the higher values, whereas the flow goes opposite to the pressure difference. And if we further derive this equation here, we further derive that we end up with something like this. So it's gonna be dp. So basically we assume it's an infinitesimal zone, then we end up with dx rho g, right? And hold on, I think I'm wrong on this. Sorry, I think we have to do that again. Sorry. 这个是 z 方向的，不好意思。Okay, here, so we are going to derive Richard's equation as well as the solute transport equation. Are two equations used particular for groundwater model and including the unsaturated soil. And later we will go through the input for USGS Sutra, a numerical model that simulates water flow in variable saturated condition and variable density, plus the solute transport processes, and see how this has been how the equation has been implemented to the input files. Before we start with everything, we need to have a basic understanding about how water flows. So think about really a 1D problem here. So if you have a simple space, and on both sides you end up with different pressure. So here would be P1, the other side would be having P2, and this is basically dx, or I can call it x1 and x2. So because the pressure on one end is higher than the other side, obviously the flow is going to go to this direction. And to be able to describe the flow, the equation is going to be written as first is the pressure difference, P2 minus P1, x2 minus x1. So that's basically the pressure difference divided by the distance between the pressure points, and that actually ends up with a value greater than 0, isn't it? If you do that in a different direction, let's say you do that from P1 minus P2 and then x1 minus x2, you get exactly the result. That means that the way how you calculate the pressure gradient is not related to the direction how you calculate how you do the derivation. So if this one comes into a definitesimal area, so when dx is very, very small, actually we would have this is equal to dp dx, right? Right. Now, the pressure gradient, so this is basically the flow direction. And we also have the gradient. The gradient actually goes on this direction, right? And obviously, flow is opposite to the gradient, and the Q has to be written as a function of negative dp dx, right? The negative here is basically to change the direction opposite to the gradient and multiply by a coefficient k, right? And that's basically Darcy's law. So Darcy's law is basically tell you that how pressure is able to drive flow from one location to the other. And for this case here, we only have 1D problem. And in the real world, the groundwater flow is not only driven by the pressure difference, but also driven by the hydraulic head. So we could have one case similar to that, say the pressure in the inclined pipe, and the pressure on one end is the same as the other, but because the height here is higher than the second place, then flow actually going downward. So that is also possible, right? So to derive that equation, we actually have to define something we call a hydraulic head. And the hydraulic head usually use psi as the input then psi is going to be equal to P divided by rho G plus the elevations, right? And you could also write it as a pressure head. That means it's going to be rho G psi is equal to P plus rho G H. Now let's think about this case. We would have pressure here as P1, the pressure 2 as P2. Yeah, and then we basically look at the vertical flow, and in terms of the gradient, if we look at the delta rho G psi, that is going to be equal to P1 plus rho G H1 minus P2 minus rho G H2 divided by, call it delta Z. Okay, so that's basically the Z directions. And to simplify that, we would have P1 minus P2 over delta Z plus rho G H1 minus H2 delta Z, right? Okay, so as we did before, this is exactly the dP dz, right? But how about this? So if we look at H1 minus H2, that's exactly delta Z. So this term could completely be crossed over, and then that is going to be equal to plus rho G, right? So in the Z direction, that looks slightly different. So if you look at the Darcy's law in the Z direction, then you would have QZ is equal to negative K dP dz plus rho G, right? And the G here is basically a scalar. This is a scalar, right? Now, if you think about this, a 3D problem where you actually have flow going into 3 different locations, so you obviously need to combine all things together. Then what the equation looks like. We need to also expand the hydraulic conductivity here as well. So in that case, the Q is going to be a vector which has 3 directions, is equal to negative K double bar. This is actually the permeability, so I want to add the unit here as well. And the other thing is Kr, which is the relative permeability as compared to the saturated condition. So this value changes from 0 to 1 based on the hydraulic head, right? And underneath, you actually have the viscosity. The viscosity has a unit of kg, meters per second, right? And on top of that, you would have the pressure gradient. So pressure gradient, so this, if we write it in a full term, it is going to be equal to dP dxi plus dP dyj plus dP dzk, right? So that's basically the whole thing. And what we really want now is that we need to have this P, but on the other side, we need to make sure that the rho G here is being added at the K term here. So how can you do that? We need to first define a G that is directional, and that is actually 0I plus 0J plus what? The K direction is going to be negative 98.1 K in the Earth condition, right? So to be able to end up with exactly this term, then it is going to be Z negative rho and G. Remember, when we are working on the Z direction, the G here is equal to 0.98, and two negative cancel each other, ends up with the positive, and this term here is not going to be influenced in the X and Y direction, and so that the hydraulic head, the elevation itself is only implemented in the X and Y direction, not in the Z. So if we look at this equation here, in terms of units, so here pressure usually comes with a unit of kg, kg why this one is here now? So kg meter square I think there is some technical issues here. So joule pen mode, create joulings only, yeah. And then the gradient here also has a unit of meter over 1. So if we look at the whole thing, so here is in the numerator and here is in the denominator. So we can basically write the whole equation here. So that has not got unit, meter square, kg meter per second, and meter and square over 1 over meter, kg meter square. Then what you have is kg is being crossed out, this is being crossed out, and this tiny thing here is being crossed out, and the second here is also being crossed out. Then what do you end up with a unit, meters per second. This is actually the unit for the Q, right? So that's basically how you know, at the 1D case, at the 3D case, how Darcy's law is being formed here. Just give a bit more details on the equations, how everything works. So when you see the intrinsic permeability, this is actually a tensor. So the tensor actually is going to be a 3 times 3 tensor, and you also have the kxy, kxz, blah blah blah, right? So why do you need to have a tensor to describe the permeability? This is because that in some of the soil material, it's not actually homogeneous. So when we're talking about homogeneous, it means that the hydraulic conductivity in every direction is going to be exactly the same. So you can pretty much draw a spherical thing here. So the X direction, the hydraulic conductivity is the same as the Y direction, and the Z direction is going to be the same. But imagine that we sometimes work with rocks. So the rock material would be something like that. So the vertical hydraulic conductivity is very, very small, right? It's almost like equal to 0. Whereas the Kx here is going to be quite large. And if you look at the tensor itself will look something really like a kind of ellipse, right? And that is able to properly described by the tensor here. The second thing here is that the Kr, as said, is basically the relative permeability, and the relative permeability is usually decreased over the desaturation. So if we draw a curve, say saturation, and here is the Kr. So if the soil is fully saturated, which is 1 here, this is 0, the hydraulic conductivity, the relative permeability here is the highest value, which is going to be 1, because so many water in the pore space interconnect together, so that if you have water comes from one end, it will move to the other end straight away. Whereas if the saturation is very small, the saturation is very small, the water is not able to find out a continuous path to go out from the system, so that the permeability becomes very low. So this is basically something related to Kr. The other interesting thing that I normally make as a kind of similarity is that when you spill water on the table, at the very beginning it goes very slow, but the wetting front always try to figure out its way to drop from the table. Eventually, once it finds the path to drop on the table, when you add more water from the one point, it just straight away go from the wetting path and drop out from the table. So it's kind of very similar thing. And basically that's the Darcy's law here. Now we need to think about how we can apply Darcy's law and convert that into Richard's equation. So again, what we have here is going to be a box, right? The box has a finite size of delta x, right? We think about the flow. So on one side, the flow is significantly large. Let's call it Q1. And on the other side, you actually have the flow that is very small. That's Q2. And let's just draw like really a kind of 3D box. So here is going to be delta y, and here is about delta z. And then we can basically write a mass balance here. So let's try to make the arrows relatively more clear, because it's somehow not really related, not able to see. So in this case, what we have is basically Q1 minus Q2. Let's do it another way, because if we do so, then the delta x is going to be negative delta x rather than delta x, because it's going to be x1 minus x2, which obviously ends up with a negative. So let's do the other end. So it's going to be Q2 minus Q1 delta x, what, times delta y times delta z, right? It's going to be the storage. So if you think about this box here as a small swimming pool, and now the flow actually, inflow is higher than outflow, what happens? The water level is supposed to increase. And the way to write down this is going to be, say, delta x times delta y times what? Times a small increase of delta z. So let's call it delta h, right? And of course, here you end up with a unit of meter cube, whereas on the other side, of the equation, you end up with a unit of meter. So that's going to be meter square, meter per second, meter. And of course, you have to multiply that by a delta t. So this is going to be second. And then the final unit, meter per second. Sorry, this is going to be that. Oh, hold on. This is not right. So this is not needed. Okay, that makes better. So the flux as a unit of meter per second times meter times meter times second. Then these two cross out. These two cross out, ends up with a meter square, and on the other side is also meter square, right? Basically tells you that the difference of the inflow and outflow caused the rise of the water level. Then we can just quickly rearrange this equation. So we move this to the other side of the equation and the delta t to the other. Then we end up with something like a Q2 minus Q1 delta x is equal to delta y delta H divided by delta Z, isn't it? Okay, so the delta Y here needs to be moved out as well. So these two terms basically cross out, right? You end up with something like that. And also, of course, you would have the delta T. So the delta T goes here, isn't it? Now, if you think about how to explain, physically explain the situation here, Q2 minus Q1 over delta H could be described by dq dx, which is exactly what we did before. The second thing here is about the term here, delta H and delta Z. We know that delta H here is going to be actually the delta H here is going to be a negative value, because let me see whether it's a positive value or a negative value. It's actually a positive value. Yes. So the flow. Yeah, it is a positive value. So let's thinking like this way. So now basically, because Q. Oh, hold on. In this equation here, because delta H is going to be positive, whereas the Q2 minus Q1 ends up with a negative value because the Q1 here is higher than Q2. So you actually have to add a negative symbol here as well, isn't it? Let's just repeat this again. So if we use Q2 minus Q1, this term will be a negative. But as a result of Q1 is greater than Q2, the water level is supposed to increase. So to be able to balance everything out, we need to have a negative symbol here, right? And negative symbol makes the term on the left-hand side as a value greater than 0. And we know that delta H is actually greater than 0, so the whole term here is greater than 0 as well. So we can't ignore the negative point here, which is the thing that I was looking for. So here, now the second thing we need to think about is how to explain delta H over the delta Z in this small section here. So if this is a swimming pool, the delta H is able to tell you the delta H is to tell you the rise of the water level within the swimming pool. But if you think about this is a porous media, now a small rise of the delta H would actually add water inside the domain, and this could actually be described by the change of porosity times saturation, which is equal to volumetric water content. And at the same time you would have the total volume included. So we could multiply the total volume together, so like this, right? And so basically the delta H over delta Z is to describe the change of the the change of the porosity multiplied by the saturation multiplied by the volume. Literally, it's basically the volume change of water inside over delta T, right? Again, we would have this term canceled out each other because we are not supposed to have significant change of the volume. The change is only about the water content within the domain. Then we end up with the standard. And at the same time, if we also include the density impact inside, than what we have in here. So let's try to implement the density flow. So without density flow, we end up with a 1D equation like this. Okay, and if the density flow is considered, so we basically assume that density could somehow be changed because of the flow density is different, we would have is equal to epsilon epsilon SW rho dt. Yeah, so this is basically a 1D Richards equation that we are trying to describe here. And if we are thinking about 3D process, and obviously the gradient here, the differentiation over x direction is going to be changed for three different directions. So the whole equation, write it up again, is going to be epsilon SW rho dt is equal to negative rho q. So when you see that there are two underscore here, each of them are actually a vector, they add up together, ends up with a scalar from a dot product. And on here, in the other direction, you also have a scalar, and then it ends up with some what we call Richards equation. All right, that was it. Okay, everyone, welcome back on board again. So we just keep going with the discussion we had in the morning, where it's about the derivation of Darcy's law plus Richards equation. And so now we are basically talking about how Richards equation is being solved. That will say how the chain rule is differentiating the term associated with t. We've already discussed how this term is being formed, so then it's this section. And after that, we will also briefly talk about what is Solute transport and how that's being solved. After that, we were talking about the basic boundary conditions for the problem. After the boundary conditions being discussed, we are talking about the input in Sutra model, and we'll see exactly how the function has been implemented into the Sutra code. And the final thing, we're talking about a specific case which involves tidal forces, seepage, and evaporation taking place. That's the plan today. So come back from the last sessions we have discussed. It's about the Richards equation we have here. So on the left-hand side, it's basically the change of the storage over a finite volume, and on the right-hand side is basically the fluxes. Now let's think about how we can further differentiate this equation in the program. So if we look at the temporal term, it basically writes as epsilon SW rho, which is the water density, dt. And using the simple chain rule, we end up with what? SW rho d epsilon dt plus SW epsilon d rho dt, and plus which term? Okay, saturation, basically epsilon rho d SW dt. Right. And what we need to know what we need to know clearly is that Richards equations solve P, pressure. So as long as you solve the equation, you end up with a P within the problem domain. So everything has to be written as a function of dp dt, and that's basically the goal we need to go, right? Now we need to look at exactly which term, what function it is associated with. So look at the very first term. The first term has got the d epsilon dt, and we know that the epsilon is basically the porosity, and the porosity, what force could potentially change the porosity? It's actually the effective stress, because if we look at the soil domain, we would have particles, and then we've got water as well. So the rest of them are basically water. So if you look at any interface here, let's say, yeah, so any forces that is acted from the top is what we call total stress, right? Once it comes with total stress, it has to be balanced by the internal force that is within the soil. And they have two sections. One is the section that is between the particles, for example, like here, 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 and here. So this force here is usually called effective stress, and that's normally written as this. And then you also have the pool water pressure, which is located in here. So that's basically pool water pressure. And based on that, what we have is total stress is equal to effective stress plus P, right? And from this equation, we also can see that when there is a change of the porosity, it is primarily induced by the force that is acted in between the solid matrices, and that's particularly the effective stress. So to be able to describe that, the equation is going to be written as SW rho d epsilon d sigma effective stress d epsilon, the effective stress dt, right? And in terms of the second, we will back visit that. So we first finish this section for now. We'll back visit. So I still use the square, the equal here. For the second term, what we have is that the change of the density. So what are the parameters that would potentially change the density of the water? It's essentially the concentration, isn't it? The second thing is that if the pressure change, that will also squeeze the density and make the density stronger. But these forces could be quite small anyway. But we still need to write that equation. So this term, if we want to further expand, it's going to be SW epsilon d rho dc dt, and plus SW epsilon d rho dp dt, right? So essentially the term here is talking about that when you add salt into the solution, the density is going to increase. And this term here is talking about when the pressure increases, the pool water increases, the pool pressure will squeeze the water particle, and eventually the density of the water is going to increase. Basically two separate processes. And the last term we have here is the SW dt. So that's pretty straightforward. It's going to be epsilon rho d SW. And what will change the SW? Soil water retention curve. So that's going to be the SW dp dt. So that's basically the further result that we end up with. Okay, going back to each term we have here. So we just have discussed that what is the force distributed within a soil domain, which is total stress, effective stress, and pore water pressure. But now this term becomes very difficult to solve because in Richard's equation, we are not solving effective stress. So we can't really tell you how the effective stress change over time. We only can tell what the pressure change over time. And we are in Richard's equation, we are not trying to solve the stress at all. So what we can do is basically establish a relationship between the effective stress and pore water pressure so that we don't have to add another equation on top to solve the stress. The basic idea we're trying to, the basic assumption we made here is that the change of the total stress during the simulation is going to be 0. And that makes this is equal to delta P. And what does this relation mean is that at the local location, anywhere like this interface, the change of the pore water pressure is always being equal to negative of the change of the effective stress. Yeah. So in that case, we can, so let's put this one as 1, 2, 3, 4. So in terms of the very first term, we can write it as epsilon, sorry, SW, rho, d epsilon, the effective stress, dt is equal to negative SW rho d epsilon d psi epsilon e sigma dp dt. Right, so basically we end up with a pressure change over time. But how are we going to solve this, the d epsilon d sigma? There are two things that we need to do on top of this. The first thing is that we would have oh, there you go. Yeah. We all know that the the solid particles is not going to be squeezed by the pressure. So what does it mean here is that the d volume of the space minus the solid area, right? So that's basically the solid area over the pressure is equal to 0. And if again we do the chain rule, what we end up with is going to be 1 minus epsilon. So 1 minus epsilon dVOL dP plus, sorry, minus VOL d epsilon dP is equal to 0. So that's basically the condition 1 we have here. The second thing that we can declare is a typical compressibility of the soil. So this could be written as, this is nominated as alpha. Alpha is equal to VOL, which is the volume of water in the domain, minus 1 minus epsilon VOL over the effective stress. So what does it mean here is that the numerator here is basically the solid space, and this will be changed based on the effective stress we applied in between the solid grain. So the whole term is basically the ratio, the slope of that curve, and the VOL is basically to normalize that change. So basically everything end up with Pascal and a unit that is Pascal over 1, or equivalently kg meter square second. So it's kind of to uniform the whole pressure. So what does this tell is that effective stress does change the total volume of the solid, which is called solid matrix, and this is basically the rate. And when we have got these two equations, we can back visit the term we had before, which is the epsilon and the sigma. And so the first term, just trying to lift it up. So this is the term that we need to solve. We actually, I think I have to stop here for a while. And in the end, we just need to put this equation back into this equation here. Then what we end up with is that 1 SW rho d epsilon d square and the sigma prime dt is equal to SW rho alpha 1 minus epsilon in the bracket dp dt. So this is something associated with alpha. Now go back to the second. So that's basically related to how you, the effective stress is potentially be able to reduce the skeleton volume, and that's very important, particularly when you have saturated aquifer. And once you have the saturated aquifer, every add up of the pressure will reduce the total volume and eventually release a bit extra water, and that extra water will squeeze the volume of that particular layer. Now if we move to the second term here, what we need to solve is the d rho dc, dc and dt. So again, Richard's equation is not solving C at all. So this term we basically assume its known property, and the C is basically calculated from solid transport equation. So how about d rho dc? D rho dc is basically the change of the concentration. So we all know that if the if we add more salt into the solution, the density is going to increase. So in most of the cases, we would have a linear correlation that says that the rho dc is equal to rho 0. Sorry, it's actually, so the rho is equal to rho 0 plus the rho dc C minus C naught, right? And this term, if we're talking about solid chloride, it's roughly 702, right? So that's basically how actual density of the liquid water is changing along with the addition of salt into the system. So basically the second term is being solved it's an explicit term when you only solve the pressure, because this term is nothing to do with the pressure. Now the third term, that's also a tricky term. So we just put it down here. We just put it down here. So what you've got here is SW epsilon SW epsilon d rho dP dP dt. Right, that's basically the third term. And for this term, we need to know that pressure basically change, the density basically change with the change of the pressure, and the concept we have, the definition we have, is actually the water compressibility, which is rho over 1 d rho dP, right? That's the term here. So if we put this term into the above equation, what we end up with is SW epsilon beta rho dP dt, and that's about it, literally. Now if we move to the very last term, which is epsilon p dsw dP dP dt, right? How to solve that? This is basically to check how the saturation is being changed over the pressure. And how can we get this? This term is actually related to soil water retention curve. Remember that I'm just trying to quickly describe what soil water retention curve is about. So let's draw a curve here. So this curve is related to how pressure is affecting the saturation, which start from 1 and right on is 0. So when the pressure is positive, that means the void space is fully occupied with water, and of course the saturation is always the same. Now what happens if the pressure goes to negative? So let's think about the case where you have a box, a sealed box, and the box is fully filled by sand, and internally the void space in the sand is saturated by water. So in that case, the saturation in the soil is pretty much fully saturated, which is 1. And now we start to putting a bit pressure, the negative suctions inside the box. And at the very beginning, the suction, with the rise of the suction, the saturation didn't change. And this is because of the surface tension. The water inside the box is reluctant to go. But if you keep on increasing the pressure, what will happen then is that the saturation, the water starts leaving from the system, and then the saturation in the box is becoming smaller, right? And then if you further apply the pressure into a relatively big one, you will find that your saturation becomes very, very small. But imagine if the pressure is relatively huge, let's say a very, very strong physical force. So if it's a syringe, it could be with the size of the room. All of the water inside the box is not going to go completely, because the rest of the water is being held up on by electrical force and van der Waals force, and those forces, this water basically make the soil wet, and they are not leaving the system. So this is basically what we call SWRES, residual liquid water saturation. So this amount of water can go, but they are not able to be taken away through capillary force. They can only be taken away by evaporation or heating, this kind of process. So this is a typical soil water retention curve. If we just want to expand this further, if when you get the clay material, the air entry pressure would actually happening a bit later, and the change of the desaturation over time is actually slower as compared to sand, and usually the residual liquid water saturation is slightly higher than the sandy case. So basically we're talking about a clay material like that, and here could be sand. So that's basically different properties in between sand and clay in terms of soil water retention curve. So what we really learn from this, imagine same soil given the same pressure, let's say this, you will always see that at the same suction, the negative pressure, the clay is able to hold more water as compared to sand, right? So this soil water retention curve is basically the way how you get the SWDP here, and the way of doing it is basically looking at the gradient at the specific saturation point, and you put that into this value here. So that's basically how the last term is being found out. So we basically discussed about the four term. So let's just quickly write everything up again, and then we conclude the derivation of Richard's equation. So we would have dSW, so it's going to be SW rho alpha 1 minus epsilon dP dt plus SW epsilon d rho dC dC dt, and then we also have a third term plus SW epsilon beta rho beta dP dt, and the last term here would be epsilon rho dSW dP and dP dt. And to finish it up, we also have negative gradient rho, which is the density, Q, which is Darcy flow, and then that basically solves the whole equations. And we could also write down the Q, which we had before, that is going to be negative K intrinsic permeability, Kr viscosity, and then we have here P pressure minus rho G. Right, that's basically the full term of the Richard's equation. And also we normally write these terms here, rho 1 minus epsilon alpha plus rho beta epsilon as rho SOP sorption, basically. So that further reduces the whole equations here. So that's basically the full equation for Richard's equation. So how this equation is being solved? In general case, I'm just trying to really figure out a simple, very, very simple result on this on discretization. So we go back to the discretization using first order Taylor series. So anything that is associated with dP dt is going to be P at n plus 1 time step minus P at n time step delta T. Okay, and anything that is associated with space, let's just put in a P dx, let's say just at the x direction. So that is going to be P at I plus 1 location minus P I minus 1 location at delta x. Right, so that's basically the space. So what we're talking about here is that the superscript tells about the time step, and the subscript here is talking about space. So you can think like this way. So let's say here is x, here is time, right? So you have these points here. So here is actually you call it I say I minus 1, I plus 1, I plus 1. Yeah, so the n here would be n plus 1. So there are several ways of solving it. If you assume that all the p in the space term is associated with n plus 1 time step, what you find is that the unknown here would be, this is actually I location, sorry, I location. So if you look at all the terms we have here, is actually p n plus 1 at I time step here. That's the equation we have here. We also have n plus 1, n plus 1, right? So that term is here. So basically, if you have these three, you actually have a correlation like that. So one equation, you would have 3 unknown as a function of 1 known, right? How can we solve that? Of course, we can't solve that one equation only, but for the next neighbor term, you would have another equation that basically establish this kind of relationships. So 1, 2, 3, and 4 ends up with one equation. 2, 3, so let's say relatively large one. These few set up another equation, and you end up with what we call a linear system, that every line has got 3 unknowns, and you got the pressure, you got the every line you've got 3 unknowns, and you got this term here in this location, and you end up with multiple equations, and the number of equations you have is exactly the number of nodes you have. So basically the whole equation cannot be solved individually. You have to solve a linear system, ax is equal to b, to solve the problem, right? That's basically how it's being solved. Another way, which is relatively straightforward, I might just simply use another color to tell, is that if this term is a function of n, then what will happen is that, so this is still n plus 1 and n, then in each equation you end up with a correlation like that. And that's great, because you've got an unknown at n plus 1 time step as a function of 3 knowns in the previous time step. So every single equation is able to solve as a function of previous known thing. This is what we call explicit method. And previously, the one that we were talking about is essentially implicit method. And what is the advantage and the disadvantages of these two methods? The advantage for explicit method is that all the results could be solved separately, and you don't have to solve linear systems like we have on the right hand side. But the problem really is that explicit method doesn't cancel out all the errors altogether. At the end of the day, the more simulation you do, it deviates from the solutions. So if you look at, so I say one of the example, we have the result. Let's say property change over time. If the solution is like that, let's say if the solution is like this kind of dots, and in implicit methods, although it kind of having zigzags, it follows the pattern very well. Whereas if you have a explicit method, your result could be somehow deviates with the actual solution, and then the more time step you go, the result becomes far away from the actual solution. But this is actually something related to how the algorithm is being formed. But in general, the best way to solve Richard's equation is to use implicit method by solving by using a software package. Now, we've done the Richard's equation. Then we also briefly talking about the Solute transport equation. So that's actually pretty similar to Richard's equation here. So again, you would have the change of time, something associated with time. So you would have change of, we can still do this, d rho epsilon SW, which is basically the moisture, times a concentration. So the concentration is literally a fraction. Not fraction, is mass of solute over mass of water, right? And this times T, right? So this is equal to a few processes. First is usually what we call advection. So what does advection mean? Advection is literally how the solute is moving along with the background flow. Let's imagine if you have a river, and the river has the background flow, and then you put an ink, let's say a plastic ball, and the location of the plastic ball over time is basically the time since you release the ball times the background velocity. So it's obviously associated with the background velocity, rho q is the background velocity, times concentration. So rho c here is basically the mass of the plastic ball, and obviously we need to consider the variation of it over space. And again, remember, when it's kind of gradient to q, we always need to have a negative. That basically change the flow direction, the storage in a negative way. So the second term we would have is diffusion and dispersion. So diffusion of dispersion are both driven by what we call a diffusion tensor. So plus a dispersion. So that's basically the driver. So what does it mean here is that you have two processes. One is mechanical diffusion. So that's kind of Brownian processes. Giving example, if you put ink into a distilled water, eventually the ink concentrated at one point will end up with a perfect spherical zone, and the spherical zone becomes bigger over time. So it's basically homogeneous in all different directions, which is the reason why we need to multiply that by I, which is literally a 1 in the diagonal direction. And after that, we also have the mechanical dispersion, hydrodynamic dispersion. So what does this term mean is that when again we use the releasing ink issue. So when you release ink into a solid domain like this, let's say ink is here, so it got a background flow over that direction, and over time what will happen is that the particles try to follow all the spaces downstream and expands. So at the very beginning, the location of the ink is a point, but over time you will see that it distributes longitudinally over a distance and transversely over a width, right? So downstream you will no longer see a point of the contaminant. You will see a plume, and usually the plume is kind of elliptically distributed. So in the longitudinal direction, it's always larger, as compared to the transverse direction. So that's basically the mechanical dispersions we were talking about. And the key parameters underneath would have alpha L, which is longitudinal dispersion, and we also have the alpha T. So in general, alpha L is 4 to 10 times of alpha T, depending on the problem, right? So basically that's the driver. Then this is not the driver, this is the conductance. So what actually caused the diffusion and dispersion? That is actually the gradient of the concentration, right? So you have to have the change of the concentration in different locations so that you can spread the concentration to different places. And again, we are talking about a porous media problem. Then the concentration can only transport within the porous area, and that's basically where the water is located in the domain. So we need to multiply that by theta, which is water content. And after that, this is actually the flow. The flow needs to be the two fluxes, similar to what we have before. So this is one flux, another flux, and then the volume change is associated with the fluxes into different directions. So we need to do the similar thing here to check the change of the fluxes over different locations. So this is literally the Solute transport equation. And for this equation, what we need to solve is literally C, concentration. So to solve this equation, we assume that all the P here are known, whereas C is the unknown we need to solve. Yeah. Right. So now we're talking about both. We've already talked about both the Solute transport equation and Richard's equation. Now we need to basically touch on how this is being solved. We do have a Sutra code, and that basically solves the two equations, and then we can basically have a look on how this is being implemented into the input files. So to do so, we need to download the SUTRASET we have. So SUTRASET, we've got a Linux system into a virtual box. So we need to download a instance from GitHub. So we just need to go for SUTRASET. So SUTRASET is here, and we need to know exactly the location so that we can pull them into our own computer. So git clone. So that basically clones the SUTRASET into our own computer. And after this is done, you will see a SUTRASET folder. And in here we've got the binary files pre-compiled for Windows machines, examples, and s.c, which is the source code. We're not going to go to the source code because it's a lot of lines. We basically look at the input of the source code. So go to examples. We go to one of the typical case we've done before, which is evaporation salt marsh. And here we've got the, let's say, sandy loam EVT4, so we can go there. And in here you've got a few files. First of all is the Sutra file that basically tells you what is the file name related to your simulations. So we'll just quickly look at it. So that's the list of things. What does it mean here is, first, IMP file, and we sign an IMP file as a file number into Sutra. Just use 1550 or just using whatever we normally use, and these numbers are always going to be different among other input files, and then you got a specific name of that file. So basically we specify the name as evapotranspiration sendinome.imp, and you have, because this is an input, you have to have that file in the same folder, which is the reason why we have this file here. That's basically input. That's the majority of the input, including geometry, porosity, hydraulic conductivity, dispersion, in boundary conditions, a lot of things. The second thing we have here is ICS file. ICS is actually the restart file, basically the initial condition. All the partial differential equation needs to have an initial condition to start with. So this is the place where you put in the initial conditions. So that includes, we have got two equations to be solved. One is pressure, Richard's equation, which solve P. Another is basically solve the concentration. So you need to have both P and C in there, right? Which is the reason why you need to have two matrices in there. The third file is LST file. LST file is basically restart file. List file. The list file basically tells how far the simulation goes, whether every parsing is correct. So it lists the progress of the simulation. Usually we just look at it when there is something wrong, particularly say the reason why the simulation is terminated. RST file is the restart file. Restart file serves the same purpose as the ICS file. So the idea is that if you want to run a very long simulation, you don't want to run them by one go. You want to like restart from some stage. So what you could do is to allow the system to produce a RST file for you, and you can basically start the simulation from that point. And what you need to do is basically change the RST back into ICS file, and the system will automatically know, let's start from there. The NOD file is basically our output. The output tells you all the results associated with node. This includes pressure, saturation, concentration. If you're solving temperature, then temperature result is there. ELE file is basically the result associated with all the elements. So in Sutra, basically the structure is being designed in this way. I just need to quickly give an example. So let's say you've got a system that comes with a kind of very uniform structure. So the node is always located in here, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So that's basically node. Okay, where are the element? The node basically is a point. It doesn't have a volume. It's basically where these tiny points are located. So the element is actually located in here like this. So that's a typical element. So the element would have 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So that's basically the element. So the property in there I can also write down. So the element here we would have relative permeability. We would also have the UVW, right? That's where the velocity are located. We would also have, so for the node, what we have? Pressure, concentration, saturation, temperature. So that's where the properties are located. Now, there's another thing if you look at the menu that's called cells. And what is cells? Cells is basically like this. This is the cell 1. This is the cell 2. So cell is where the one drawn in blue, and the cell number is exactly the same as the node number, but it has a specific volume. Right, so that's basically what cell is. And why do we need to have cells? Because node only tells you a specific property at that node, at that specific point, but that value is actually an average result of the cell. So when we're talking about the P, the pressure in the node, the P is actually the average pressure of the cell where the node is located. Similarly to C, SW, and T. And also remember, when we solve the governing equation, Richard's equation, for example, it has to be based on a finite space. So the space that's being based on is actually the cell. And again, the number of the equations we will have is equal to the number of node or cell we have. So for this kind of setup, we will actually have 16 equations. Okay, so 16 nodes. So basically that's where the node cell is located. So go back again. We also have observation file. Usually we don't use that much because it outputs every single time step. Basically the observation file tells you a change of the property over every single time step at a specific location. So you could specify the location anywhere within the domain. So it is useful if you have a well or the field data and you want to check it over time. The other way you can do is basically increase the frequency of NOD file and ELE file output, because it basically output all the results at the specific time step. So if that output's frequency is high, then you're still able to use this two file to find out the properties at the specific location. So in general, you can just simply use the NOD and ELE file to tell what is going on. SMY file is basically a summary file that tells you how your simulation goes. In general, how many iterations you have gone through, and also how many nonlinear iterations you will be going through on this. BCOF is basically anything associated with pressure boundaries. So you specify many pressure boundary conditions, and then this basically tell you where is the pressure boundary condition and how much flow is going through that pressure boundary. BCOF file is basically source and sink term. So the source and sink term here, is basically that you implement a amount of inflow or outflow at a node. So what is the result looks like? We actually implement evaporation through BCOF file. And the BCOU is basically the concentration change, the change of the concentration at this. It basically specify a designated concentration at the boundary condition and how much concentration change is located at the designated pressure boundaries. We'll go through that, particularly for the IMP file. You can see what is actually taking place. So before we do that, I'll just quickly tell what does this simulation do. So we draw a simple sketch to tell what is going on here. So basically the domain looks like this. It's a 2D problem. So the domain looks like this. The domain looks like this. And what does it do is basically to look at the salt distribution within a tidal creeks. Tidal creek is basically a channel in the coastal area where water predominantly transports through. And given that the place is very close to the coastal zone, the water level in the channel is usually related to the tidal fluctuations. So it increases and decreases, and at the same time, because of the tide fluctuation, the water table within the domain changes as well, right? It could go like this. And then we basically look at how water and solute distributed within this zone. So what is the interesting phenomenon here? It is that the tide moves up and down in the domain, and they will create a bit unsaturated zone in these locations. And the unsaturated zone will have evaporation taking place, and the evaporation will take the water away with salt remain. So this is basically the EVP. And over time, we want to see where is the location that salt is relatively concentrated, where the other places you may not have salt at all. So the boundary condition is being applied by no flow on the left-hand side, no flow on the bottom, no flow in here. This is basically what we call symmetric boundary, hydrological divide, because you could imagine that on the other side of it, it does exactly the same thing. So even the hydraulic distribution is going to be the same as the problem we solved here. So we don't have to repeat the whole process. We just need to assume that on the other side, it does exactly the same thing. So this is hydrological divide. Right? Now, okay, what happens on this boundary here? This is a bit tricky. So in here, what we have is actually three locations. The first location is the domain, the boundaries that are under the water level. So we are talking about here, these sections. So in this section, what we need to prescribe is that the boundary cell here has got a pressure P is equal to rho GH, basically hydrostatic, and the H is the height of the water level. So that's the PBC. And what that boundary will influence the domain. So based on that, they also calculate a pressure next to the cell, and then the flow will be calculated by K times PBC minus P, right? So if PBC is higher than the P at the boundary, what happens? Inflow. Whereas the PBC is lower than the pressure inside the node, water will go out, right? So that's basically applied in this section. Okay, what happens for the pressure on top? So let's say this section here, red here, right? You see water table is located in here, and this cell is not inundated by seawater, and yet the pool water pressure here is actually greater than 0, right? Whereas in the outside, PBC pressure is actually 0, isn't it? So that's exactly where seepage is taking place. And the seepage is calculated by P minus PBC times another coefficient K. So this is always positive going outward. You can't have seepage going inside. But this could happen if you apply the same boundary condition on top. So you could imagine that in particular in this section, the pressure here is less than 0, where the PBC is still what? 0, because it's connected to the atmosphere. And is there any flow? You can't have flow, because if you do have a flow driven by P minus PBC, then you would have a inflow, and the inflow is artificial. So what we prescribe this boundary is done by K is equal to 0. So basically no flow associated with the pressure difference. We need to force it. At the same time, we will say this is the place where evaporation taking place, right? The evaporation taking place, and then we will have a sink term to do so. The second trick that we need to sort the sink term is that this sink term will only take water away with salt left on the surface. So in general, a lot of sink term in the numerical model assumes that the solute goes along with the sink, but this is not really the case. Evaporation actually accumulates salt on top. So so basically this is the way how the boundary condition is being prescribed for this specific problem. Now we can basically go back and see how it's being implemented in the model. We just need to go to evaporation IMP file, then explain individually, right? So the first two lines is basically a comment of what the problem you try to solve. So you've got locations and a title. Then we went to the dataset 2. So what does it tell is Sutra version 2.2 solute transport. You could change the solute into heat transport so that you basically solve pressure and temperature. But for our case, it's basically solute, so you use that as solute. The line followed below is basically tell you what is the mesh look like. We are solving literally a 2D problem because we only get x and y, and it's a regular mesh. The mesh is basically the regular mesh means that even though the domain looks slightly non-symmetrical or change over the depth of the aquifer change over time, but the number of cells at each row or each column is exactly the same. Or we can use this one as example that even we have only 9 elements, we could have something like this, really. Or you have this. So even though the top is somehow tilted, the number of cells in the horizontal way and in the vertical way are exactly the same. So it's still the regular meshes. You could do irregular meshes, something like really this kind of square thing to discretize your problem. I'm just trying to roughly tell what is the unstructured mesh, but this is basically the way you have a lot of squares to differentiate your zone, and there is no kind of patterns in here. So that's a typical unstructured mesh, but we're not using it. We're using a regular mesh. So if you use regular mesh, you can tell how many nodes are there in the horizontal direction and how many nodes are there for the vertical directions, because it's basically fixed at any single lines or columns. Followed up is actually the number of nodes. So we only have 2006 nodes, and then the element is 2600. In general, my advice for number of nodes and elements is that if you're just trying to prototype, try to reduce the cell down to 5,000. This is advantageous given that you can get the result relatively quickly. And if this is something that you're not expecting, you can just simply run another model. I've seen a lot of examples where users tend to create a problem with millions of nodes and elements, and it takes so much time to finish the program, and then debugging becomes even more difficult. Remember one thing: the numerical model, the result has to be independent from mesh. So when you have a relatively coarse problem, you solve it, and still once the problem result becomes something that you would like to further investigate, you can always back visit with fine mesh, and the fine mesh is going to give you relatively similar result. So basically, coarse result is good enough to tell you information, and later on you are always free to refine it. But refine it is at the stage when all the parameter is being fixed, so it's not actually at the stage of prototyping. So prototyping, always small number of node and elements, please. The followed up numbers here is basically the number of the pressure node, which you have the PBC, which is we were just talking about the number of cells in the very top one, because the top one could have different boundary conditions. It could be source and sink term for evaporation. It could be the pressure boundary conditions. But in general, the number of cells at the very top is actually 41. So that's where the 41 comes from. So it's the same as the number of cells on the top. And why there are three? So one of them is for pressure boundary condition. Another one is for concentration boundary condition. And one more is basically the source and sink. So they are separate processes. Now, these are the keywords to tell what the model will do. Unsaturated means that the unsaturated zone flow is considered. Transient flow means that the pressure will change at each location will change over time. The transient transport means that the concentration will also change over time. And cold means it's a cold start, which means they read the input, the initial condition from ICS, and that's basically the start of the project. And the 21283 here is basically to tell you when you write a RST file. Remember, we just discussed that the RST file basically can be changed into ICS file, into an ICS file so that you can restart the program. So basically, this number here tell you at how many time steps you need to rewrite a RST file. It's, let's say, like this way: you play a game, you play a computer game, and you want to save the game. This is to tell you how long you need to save it, so that you can restart from there. Okay, so in dataset 5, you got 3 parameters. The first one is actually a number we call up. So once we set up as 0, that means the problem is actually central derived. The space. I'm just trying to use the terminology here. It's to say that the space term is to use central spatial terms, central space derivation. So the central. So to give a quick example here, so if you are basically using central discretization, you would have. So central discretization means that if you have a I minus 1, I and I plus 1. So if it's actually dp dx that term is going to be differentiated by p at I plus 1 time step minus p I minus 1 times over 2 delta x. So that's basically the central spatial deviation. Whereas if you put the up into 1, what happens is that as long as you got the flow in that direction, you know the flow direction, then dp dx is going to be read as pi plus 1 minus pi over delta x. So it's no longer about some information at the downstream, it's mostly driven by the upstream condition. This is what we call upwind spatial derivation. And way that is being used when your flow is very turbulent or very fast. Central spatial derivation is in general being used for slow process. In general, we just put that one into the central derivations. And upwind spatial derivation is actually required by solving Navier-Stokes equation. Now go back to the problem. You've got another two parameters here, 0.01, 0.01. What are these? This is actually the boundary condition, the K we prescribed. So remember that when you have prescribed a boundary as PBC, the flow is calculated by PBC minus P. But the K here is basically the conductance, and the parameter that you prescribed there is the conductance at the boundary. So the first one is something associated with pressure. The second one is something associated with concentration. Remember, we also put the concentration as CBC here. You also have the C in the domain. So basically, the flow C is equal to KBC CBC minus C, and the KBC here is actually the parameter here. Now we're talking about the time steps. So the time step to us is that how many time schedules you have, and how many time step, what is the time step, and how many steps you will run. I think the key information we want to put it here is that all the time step is actually the same size, and the time step is 240 seconds, and the total number of seconds we need to run is this number. It's roughly 9 million time steps, and usually this has got an upper limit. If I remember, it was 10,000. So Sutra is not able to run more than 10 million number of simulations. So if you need to run that long, you really need to split the simulation and using RST to restart. That's basically the trick. Now we can just move further down. So that's basically the format. So 3 ones and time steps, and then the dash at the very bottom. You could put several time schedules as well. That's more important when you would have different time step in the whole simulation. Let's say in the first week, you would like to have 1 second per time step, where later on you want to have 5 seconds per time step. So you could have multiple lines here. But in general, you can just put 1 time step here, one time step across the whole simulation. Now we end up with something very, very critical. This is the parameter that you really need to play with. This is called the iteration criteria. Before we do this, we need to know what these two lines are doing. We just briefly discussed before that that the simulation is done by setting up a linear system, and the linear system is actually located up here. up here. So that's basically where the linear system is located. So the general way of solving linear system, which we learned from university linear algebra, is to use Gaussian deanimation, which means that you're trying to rearrange this equation, like this big matrix, to something like only one in diagonal direction, so that you know the x you're trying to solve. The problem of using this method is that it's very slow, very slow. So we tend to use a nonlinear method, and the nonlinear method usually use a conjugate gradient method, which is basically look at the gradient, look at the gradient how of the solution. Just quickly give you an example. Let's call Newton methods. So imagine if we want to solve something like y is equal to fx, what you could do is to say fx plus y is equal to 0. Then we basically need to find out when the curve meet with zeros. So let's imagine this curve looks like this, right? So if we find where this point is located, we are good to go, right? Then how to find it? Of course, if there is an analytical solution, you can solve it and then you say y is equal to fx. Or let's say if you can say f is equal to this, right? But this is not really the case, and a lot of problem wouldn't have that. I'm just giving you one, say, you get screwed up because you couldn't be able to write x as a function of y. So, but nevertheless, this is actually a kind of monotonic equation. So what you do is that you just basically assume x be anything. So it could be here. Then what they do is basically look at the slope of it, and then they find this point, and then they can see where this point meet with that, and then further draw a curve, and then by multiplying this process, you will more or less end up with the location where it meets with 0. So it's basically a kind of nonlinear process. This is what we call a Newton method. Another method we normally use is what we call bisection method. So that's kind of very straightforward way as well. So again, we need to basically solve this, but we need to find out 2x, let's say x1 and x2. But what we need to find is that the fx1 plus y1 is less than 0, whereas fxy1 plus y2 plus y2 is greater than 0. So like here and here, right? So if you have a case like this, you know that your solution is going to be right in the middle. Then what we do is that x3 is equal to this, right? So you cut right in half, and you try to calculate whether that solution is greater than 0 or less than 0. So if this is greater than 0, you know that solution is no longer in this region, and you further cut it half. This method is able to find out the solution as long as you specify the convergence criteria, but it's far slow as compared to the Newton methods. And basically the parameter we describe in here, the 1000 here, the 10,000 here is basically how many iterations you should go to find out the solution. And this parameter here is to tell you what is the resolution when you iterate the process. As you can see that the bisection method could go as small as possible. So even now I'm drawing this curve, but if you zoom in, you still have a lot of curve, you still can refine it. And this criteria here is to tell you at what accuracy you need to go down further. Because the numerical solution will not give you an accurate solution. It's more about how many effective digits you want to get from the solution. So my advice for this parameter is always using this number here, right? This two number here, and never change it. Now, when you get this, and what is this one's here? What is this one's here? This is what we call nonlinear iteration. Remember, let's go back to the problem again. So we've got this problem, and we end up with a linear system, which is fantastic. But the problem is not actually very nonlinear, because if you carefully look at all the parameters we have for Richard's equation, we know this is known. Do we know SW? We may not know that, because SW is a function of P. This SW is a function of P. This SW is obviously a function of P. And the SWdP is also a function of P. The other thing is that when we look at the Q here, we know the relative permeability is also a function of P. So if you say this is a function of P, and then you have this term written by P I plus 1, sorry, m plus 1, I plus 1 minus P I minus 1, n plus 1 time step, then the P multiplied by another P, it's no longer be a linear problem anymore, right? So what can we end up with? A linear system. So the idea is that for the next time step, we assume that the KR, or this term, say SW, KR, or anything, that's basically a function of P at the previous time step, which is n. So we assume it's known. And then we try to move to the next time step to calculate the P at m plus 1 time step with the first iteration. After we get that, we assign this parameter into the SW, the KR, or the nonlinear curve, and repeat that process, and then we are able to calculate m plus 1, 2. And then we again put that into the saturation and the relative permeability, and then we calculate the P again, and then we get P at m plus 1 time step, number 3 iteration. So when should we stop it? Pretty straight away. So if the P m plus 1, let's say ITER plus 1 minus P m plus 1 ITER is less than a criteria. This criteria, if it's less than that, stop doing it and then move to the next time step. That's basically the idea. So the criteria here is being specified by the number here for pressure, and this for concentration. And how many iterations we can go further, it's being specified by that. We are saying 5,000. So if it's more than 5,000 times, that means don't do it anymore. The simulation failed. So we basically gave these parameters. My advice on this is that, first of all, you always need to enable nonlinear iteration, because Richard's equation and solid transport equation are all nonlinear. We want to make sure those nonlinear term is as close as the solution. We don't want them to differentiate too much. But the parameter, the number here, is subjected to change. So if you find you set the you set the values, and then you find later on it doesn't converge, you just try to increase 1 order of magnitude or even 2 order of magnitudes to see when you end up with the convergency. And as you can see, if you set the criteria, which is the equation here, to a relatively large value, you will always not doing any nonlinear iterations anyway. So eventually, if that number is huge enough, you wouldn't need to do the nonlinear iteration anyway. So always try to enable the nonlinear iteration, And if it doesn't converge, reduce one order of magnitude until you actually end up with a good solution. And sometimes the pressure change could be quite significant. The reason we actually have 8,000 here is because when the soil is fully unsaturated, like very, very dry, the pressure is extremely large and negative. It's extremely negative. It could be negative 5,000. So I'm just showing you from the soil water retention curve here. So when the soil is very dry, where is the soil water retention curve? It's not, that's not the one. Is that? Soil water retention curve. Okay, that's here. So let's say when your saturation is, the soil is very dry, so your saturation level is here. So the pressure here could go up to this Pascal. And once the water, the seawater comes, the pressure on top is actually a positive value, right? So the pressure change at that small time step could move from negative 10 power 9, this is 10 power 9 actually, to some positive value, and that could be quite significant, even much more than the criteria that we specify here. So this is pretty much like nothing. And same thing applies to the concentration thing as well. Okay, so that's basically this term here. This section is basically the number of output you need to put in. So the 20,000 here is related to the type of the output on the screen. So you can look at the menu to see what type of output you would like to. This one is about the NOD files. So the NOD file is specified in this. So all the node related result. And here we say that you plot out the node number, the x coordinate, the y coordinate, the pressure, concentration, and saturation. And the line followed by that is basically the element files. So it's ELE here. So in the ELE files here, the output is going to be the element number, the centroid of the element, which is the middle point of the element, velocity in the x direction, and velocity in the y direction. And these four files here is basically related to the frequency of output in the boundary files. So that includes BCOP, BCOF, and BCOU, right? Now we move further down here. Well, this one doesn't have a unit, but I'm trying to remember really. So the 0 here is actually the aquifer compressibility. Aquifer compressibility we've already discussed. So this is actually the alpha, we have it somewhere. The alpha was described in the SOP. Yeah, so that's where it's located. And the alpha is basically here. So this value is usually 1 power negative 7. And we move down further. So this one I remember was heat capacity. So in the soil, the heat capacity could always set as 1 if you're using Solute transport equation. So the E minus 7, the E power minus 7 here is the mechanical diffusion. So this mechanical diffusion is specified in the Solute transport equation here. So that's the mechanical diffusion parameter. So it's one single parameter. In general, this value starts from 1 power negative 9 at 25 degrees Celsius. The reason that we set this one relatively larger is because that when you have the evapotranspiration concentration, you actually need to have relatively, the concentration gradient could be quite sharp particularly at the location where evaporation is relatively strong. So, but this causes simulation challenge. When the concentration gradient is strong, then the flux becomes bigger. Then the way to avoid having relatively fine cells is to enlarge the mechanical diffusion. So basically, this is the parameter here. The 1000 here is basically fresh water density. And for the 0 here, I don't remember. I don't remember what this 0 here means. But we can pass it in general. I think it's something related to the heat transport equation. And 713 here is basically the rho dc, and the rho dc from the equation is located in here. That's basically 702 as we discussed. Now let's move along. Viscosity. Viscosity is located in Darcy's law, and that's actually in here, right? So for fresh water at 25 degrees Celsius, it's 1 power negative 3. Keep going. Okay, for this line, let me see. So the first value here is related to the aquifer compressibility, which is beta. And the beta, can we actually do this? I think we can split the screen so that we can see both sides. So the beta is located in here, right? The beta. Usually that number is 1 power negative 9. The reason that this 2 is not being specified in our simulation is because this is relatively shallow aquifer system, and the compressibility in the lower section is usually very, very marginal. So we just simply specify it as 0. And these 2 zeros I didn't remember, but it's not related to the do you have them? Fluid diffusions. Oh, okay. So this is basic value of solute base values. So this is base value of solute concentration or temperature at the base fluid density. So for us, the base concentration is actually 0. So we specify it as 0. And we just move down here. So the 2600 here is the solid density, the particle density. So the unit is kg per meter cube. The Frederick here is actually adsorption. This adsorption we didn't discuss in the solute transport equation. So basically it tells you that when the concentration goes, the solute goes into the soil matrix, some of the concentration will be attached at the surface of the solid grain. It will not go away, but eventually when the ambient environment becomes relatively fresh, those attached particle will eventually released back to the aquifer, to the pool water. And the reason that we specify this here is not actually to simulate the adsorption, whereas we try to use this mechanism to store solid salt. So basically, salt will start precipitating at 265 degrees Celsius, 265 ppt, which is a concentration of 0.265. So we basically use an exponential correlation established by Frederick correlation. So by using this exponential way, the adsorption was quite small, or nearly 0, when the concentration is less than 265 ppt, where it increases potentially to store the solid particles when the concentration go beyond 265 ppt. So that's basically the way how we store solid salt in the system. Later on, we have the dataset 12. Dataset 12. These zeros, it doesn't relate to. Okay, so that's actually the productions and productions in the domain. So this is not related to our problem. We just specify as 0. And dataset 13 here is actually the vectors for gravity. So the gravity for us is y and y direction, and it's facing down, which is the reason why you've got the negative. Dataset 14a here. Dataset 14a here is related to the node location. So the first line here is actually our overall scale. So it starts with a word node to tell the system that you are start of dataset 14. This 1110.913 is basically our overall scale of x, y, and z. So when you see from the dataset 14b, which is followed by the first line, you would have the first is the node number, the second is associated soil particles, delta x, delta y, delta z, and porosity. And sometimes you really want to overall expand or reduce the domain. You don't really have to change every single line. You just need to multiply the whole thing by the factor here. So you basically expand and shrink if you want to. That's for the y direction, that's for the z direction, and here is for the porosity. So it's an overall scale for you to easily configure. Now, the tricky thing is about the number 2 here. So what does the number 2 here mean? Number 2 for here is usually, I think the variable in the code is say nreg. So this is to tell you what set of unsaturated parameter you need to use, because in some cases you would have the heterogeneity where soil in one domain is different from another, and those soil would have different unsaturated permeability parameters. So you could specify 2 groups, one for sand, another one for clay. So then you just need to specify which parameter this node will go to. So the number 2 here is to tell that go to the category 2 of the soil water retention parameter and use them. And you could also specify a number 1, which could be sandy, and then the parameter will automatically go along with the first set of unsaturated, the soil water retention parameter. So that goes to the dataset 14b. So those things are normally computer generated. So you could use Argus 1 or you could use SUTRAPrep and then further change it. So for our problem, the x direction is changing, the y direction is related to the gravity, and the z direction is always the same, which is the reason why it's a 2D problem. And this is actually that one is actually the thickness. So we need to basically move down relatively quickly because the number of node here is quite significant. I think it's 2000. Now we move to the element related issues. So it's the same principle. We have the element starting with a value element, and then you would have all the overall scales. So this is the scale for horizontal hydraulic conductivity, and the horizontal hydraulic conductivity is being specified in this file here. And the second is the vertical hydraulic conductivity, and that multiplies by 10. So as a hydrogeologist, I think you always need to have a rough idea of what the hydraulic conductivity represents. So for me, if the hydraulic conductivity is 1.2 negative 12 times I scale of 10, so it's 1.1 power negative 11. So you know this is very, very sandy actually. Whereas the value becomes smaller, you know that it's becoming more like clayish material. And then you've got another two parameters here. So we're just trying to describe this one by one. So the first one is that how the principal hydraulic conductivity is tilting from the original location. So here we say 0 degree. That means the x is just in parallel with the horizontal direction, whereas the vertical is in perpendicular to the horizontal direction. So it's a kind of Cartesian axis. But you know, sometimes if you have got a fault, so if you got a fault, then when we draw a spherical a ellipse, so basically what we were talking about here is that the saturated hydraulic conductivity forms a perfect perfect sphere. But in some of the other cases where you have fault, where you know the sedimentation is done by that layer and later on it's being tilted, and then the tensor for saturated permeability is going to differentiate it with a theta here. So that theta here is associated with the 0 you prescribe here. These rest of the values here are related to the longitudinal and transverse dispersivity, which is the thing that we discussed before using this one here. So remember, the longitudinal dispersivity is always higher than the transverse dispersivity. In our case, it's actually one order of magnitude, and that multiplied by a coefficient. So basically here is 0.4, and this one is 0.04. So that basically tells the dispersivity. If we go back to here, the elements, we also need to have the element number for sure, and that one number here is again related to the soil water retention parameter. So we are still using 2 because this number 2 here is intercorrelated. That refers to the same type of the soil. So in some cases where you would have different heterogeneities, so the heterogeneity is being differentiated by the number 2 here. So we move further down. Then you would be able to see the final result, the final input. Oh, sorry, we have yet arrived the final input. We still have the boundary condition to describe. So the boundary condition started with dataset 17. Dataset 17. So in our case, we would have we previously prescribed. So this one is set start input 17. So I just need to go back to here using INP 17. So remember that at the very beginning in dataset 3, we said that in dataset 17 there are actually 41 number of boundaries that will be source and sink, and the source and sink is related to the evaporation on the very surface. So here we need to tell the system exactly where those boundary conditions are located. So we go to the INP 17. Sorry, INP 17. Then you will see that 1, 2, 3, 4, 5, 6 up to 41 are all the source and sink term, and those term is these cells are all located at the very surface of the domain, which is here. So the negative here means that we don't want to give the result from this spreadsheet. Instead, we want to give this result. We want to give this result to the BC time, which is a user-defined boundary conditions, so that we can use we could simply use a bunch of fortune code to tell how much water will be evaporated at a specific location. So that's related to the pressure boundary conditions, the source and sink terms. It ends up with a 0, and then we move to the number dataset 18. So dataset 18 is related to the the source and sink for concentration. So it basically only subtract the concentration out without change the water level. It's a kind of pure filtration system, but we don't have this type of boundary, and that's the reason at the very beginning we've got a 0 here. The 0 basically tell you that in datasets 18 we don't have any. So we can go back further. So we're talking about dataset 19. Dataset 19 is basically the pressure boundary condition. The pressure boundary condition is being prescribed by the equation here. So we have this. So this is the pressure boundary condition. We need to tell exactly at what node this pressure boundary condition is being located. Is being located. So we again describe the very surface condition, the very surface as the pressure boundary conditions. So that again goes to 0, 1, 2, 3, 4, 5 up to 41. And after that we move to dataset 20. Dataset 20 is actually the concentration boundary conditions. So that's being driven by the equation here. So CBC minus C times a KBC, and these numbers here again is on the surface because we want the concentration chain, the concentration boundary applied on the surface. The final thing we have here is basically the correlation between the cells. Again, this is automatically generated. So the idea of this line is that when you draw a mesh similar to this, similar to what we have here, so the number 1 here is associated with the element, so that's basically the value right in the middle, whereas this is basically a counterclockwise number of the index of the node. So let's say here would be, if it's this case, it would be 1, 5, 6, 2. Then it moves to the second line, we'll say number 2, that would be 2, 6, 7, 3 in here. The number 3 here would say that 3, 7, 8, 4. So by doing this all the way down, the system needs to understand which is the neighboring nodes and which is the neighboring elements, and then you create a integrated domain. But those numbers are not generated by hand for sure. You need to use the external plotting system to create that. So that's basically about the IMP file, right?